Mute can also apply to video. All the technology I've used in my life, that's a first. Right? So now you know about the quiz. We are covering 11.3 today, rates of change. That's what was wrong last time as well. That other tech guy, whose job to fix this stuff, didn't know that. You know? Muted. Okay. So we're talking about rates of change. Here's a chart, right? It has the distance traveled in miles and the time in hours. So I'm going to call this function d of t. They use s. A lot of times they use s to measure distance. You understand why in higher level math, but I'm going to use d. So t is time in hours. So you can see that, let's see, after 3 hours, we traveled 168 miles. So your average speed, right? Like when you drive, you might speed up, slow down. You're not driving exactly 55 miles an hour the whole time, right? You speed up, slow down, right? But you would have an average speed. So the average speed is what we would look at. We'd say, well, we traveled 168 miles in 3 hours. And whatever that refraction is, that would be the average speed. Does that make sense? But what this is here, where we get that is we'd look at the distance at time 3 hours minus the distance at time 0 hours. That's 168, right? So it's 168 minus 0, right? 168 minus 0. And then it's divided by the change in time. So we do 3 minus 0. So what this is this is like remember your slope? Your change in y over your change in x. Y'all remember that? Right? And that's for a straight line. A straight line, the slope is the same everywhere, right? Okay, what we're going to learn is that you could have something that does this. Okay? And so, we could pick it at this spot. Let's say between A and B. So, there's f of A, and here's f of B, okay? So when you're looking at this, the change in y, the change in the output, this is your f of B minus f of A, right? That's your change in y. And then, let's see, from here to here, this is B minus A, this is your change in x. So what we're going to say here is that that line right there, the slope of that straight line is the same as the average of the slope of the curved line. See, the curved line, the slope is different everywhere, right? The slope is constantly changing. Well, the average slope of that happens to be the same as the slope of this straight line. All right? And we're going to use this trick because, yeah, this tells us the distance, right? It didn't give it to us, but there would be like some stuff with t's in it over here, right? A function of time. So if you have a position at a given time, what we really want now is we want another function that tells us the velocity at any instant of time. Yeah, the average velocity is great, but our goal here is to get to, I want a function that tells me the velocity at any time. And if your velocity is changing, then that means you have acceleration, right? So your change in distance is your velocity, but your change in velocity would be your acceleration. So I also want a function that tells me my acceleration at any moment in time. And it keeps going. If your acceleration is changing, they call that the jerk. That's what gives you whiplash in your car, a change in acceleration, right? If you accelerate, you just get pushed back. But if your acceleration is changing, you get whiplash. And the change in the change in the jerk is called the snap, and the change in the snap is called the crackle, and the change in the crackle is called the pop. Literally, the snap, crackle, and the pop. In physics and stuff, you'll never ever see that. We basically stick with distance, velocity, and acceleration because all those other terms basically end up so small that they fall out of the equations. So this is our goal today: is to figure out to turn this into an instant of time. So you can see what we could do is like, what if I wanted to know the slope right here? right? Right at, what if I wanted to know the slope right at this point? What I could do is I could drag this point and this point to get closer and closer and closer, right? So instead of looking at this big interval of time, if I want to know what the slope is right there at that one point, I just drag A and B to that point. So I look at this little bitty time, this little interval. In this case, it's a time interval. Okay. So what I would do is I'd look at a very small, uh, and I call that H. It's a very small time interval. Okay. So you can imagine, let's say you have video of somebody running, right? If you just have a snapshot, you could see the distance he's ran, right? You could see the starting line, where he's at. You know the distance, but you have no idea how fast he's moving, right? But if you have like a short video clip, and let's say the distance is marked on the ground. So a short video clip of like 5 seconds. You could see, oh, he traveled this far over those 5 seconds, right? So his average speed in those 5 seconds is whatever, right? Because you could see him moving. But that doesn't tell you how fast he's moving at any one of those seconds or any instant in time. That's just an average over those 5 seconds. So what you do is you take the length of the video clip, the time length, and you let it get smaller and smaller and smaller and smaller. Again, with just a photograph, you have no idea how fast he's moving. But if you have just the tiniest amount of time, you can see, ah, I moved this far in that tiny amount of time, right? So that tiny amount of time, we're always going to call it H. And what we do is we use limits. Remember limits? We take the limit as the amount of time of that video, the length of the video, we let the time go to 0. So although we end up with just a photograph, we also get the information from it. We get the actual velocity of that instant of time. So that's what we're trying to do here. And it turns out to be pretty easy. The algebra, if you're good at your algebra, then it's simple. You're probably not. So your biggest difficulty in here is going to be the algebra, not the calculus. Okay. So here's just a chart looking at different time intervals. The same function. So from time 2 hours to 3 hours. So from the second hour to the third hour. All right. Here's the distance at the third hour minus the distance from the second hour. So the distance at the end of the 3 hours was 168. The distance at the end of the second hour was 118. So from hour 2 to hour 3, we drove 50 miles. And that's 50 miles in 1 second, right? From or 1 hour, I should say, from hour 2 to hour 3. So 50 miles in 1 hour is on average driving 50 miles an hour from hour 2 to hour 3. Or you could look at the average from 1 hour to 3 hours. So at the third hour, he's at the 168 mile mark. After 1 hour, he was at 52 miles. So from hour 1 to hour 3, he drove 116 miles, but that was over 2 hours. So divide that by 2, and that's the average speed from hour 1 to hour 3. And they just got different averages for different amounts of time. So from 30 minutes to an hour, he drove 30 miles. So you take 30 miles and divide it by a half. So from 30 minutes to an hour, he's been driving on average 60 miles an hour. So everywhere we look, it's just f of b minus f of a. And then we'll divide by b minus a. And that's what they're doing here. Here's where they just, same chart. Dang it, I know who I am. This is the same chart, but now they're just dividing by the actual interval of time. So the difference in the distances divided by the difference in the time, okay? So we're talking about change in distance over the change in time. And remember, slope was change in output over the change in input, all right? It's the same thing. I'm just calling it x is t and then y is d of t, okay? So all it is slope. It's a generalization of the concept of slope. Slope is a rate of change, right? Okay. So B minus A, that's your change in time interval. So again, I could draw a picture, say it's like this or whatever. So I could pick an A and a B. So B minus A, if this is T, that's just a change in time, a time interval, all right? And then if I did, here's F of A, and up here is F of B. So F of B minus F of A is the change in the distance. So change in time, change in the distance traveled. And you put one over the other, that's your average speed over that interval from A to B. So let's look at an example. And you'll see that calculus is easy, and it's the algebra that's hard. So here's our F of X. They want to find the average rate of change of F when X goes from -2 to 3. So the average rate of change, we're going to do F of 3 minus F of -2. On the bottom, we do 3 minus -2, right? It's the same numbers here and here, right? If you flip-flop these, that's fine. If you did F of -2 first and then F of 3, as long as you swap the bottom as well, you just get an extra minus sign on the top and the bottom. So it's still going to be the same thing, okay? So this is your change in Y. This is your change in X. It's your slope, right? So F of 3, F of X says take your input, square it, take 4 and multiply by your input and add 5. So that's F of 3. Now we want to do minus, don't forget your parentheses here. So inside these parentheses, we're going to put F of -2. F says take your input, square it, add 4, multiply it by your input, and add 5. Okay, so be careful that you want to have these parentheses because we're subtracting F of -2. This is F of -2. We want to subtract this whole thing. So you have to put those parentheses there. So you remember to distribute this minus sign to everything, right? So here's F of -2, right? Like a green, right? So that's why you want those parentheses. That's important. Otherwise, it's just totally ruined, okay? So step 1 in algebra, know what you're subtracting, right? We're subtracting F of -2. Now on the bottom, we have 3 minus a -2. That's 5, right? And you can see that over here is -2 and over here is 3, right? The change in the input is a length of 5, obviously, right? So let's do this. Let's see. 3 squared is 9. 3 times 4 is 12, plus 5. -2 squared is 4, and then another minus. We're subtracting. 4 times -2 is -8, and then our minus makes it a +8, and then a -5 all over 5. So +5 minus 5 go away. 9 and 12 is 21, minus 4 is 17, plus 8 is 25 over 5, and we get 5. All right. Now, this stuff up here was in miles, right? And this stuff down here, the time was in hours. So the average is 5 miles per hour. Okay, well, that was a different example. If it was like hours and those were in miles, it would be in miles per hour. Here, they're just talking generically. All right, so we don't have units. So that's the average rate of change of F from -2 to 3. Uh, Dow Jones, let's look at this example here. So here's our chart, and I think there's a question somewhere here. There it is. We'll do part A. Approximate the average rate of change of the DJIA with respect to time over the given intervals. So from 2013 to 2015, okay? So we want to know the average change. So here's 2013 and 2015. we go up here. Now we could look at the chart and estimate it, but at the graph and estimate it. But the chart here gives us a much better numbers. Okay, so I'll call it D for DGIJ. So the DJIA at 2015, and the same thing at 2013, and then the difference in the input. All right, difference in output over the difference in input. So at 2015, let's see, here it is. It's 17,833, and at 2013 it was 13,413. 2015 minus 2013 is 2. So the difference here is 4420 over 2. So that difference is just 4420. So what it's saying here is from 2013 to 2015, let's see, from here to here, we've gone up 4420 in 2 years. Okay, so 4420 divided by 2 is 2210. So all we're saying is the DJIA changed 4,420 points or whatever this is in 2 years. So if it changed by this much in this amount of time, the average change is by 2. That makes sense? Okay. And as you can see here, there's a straight line. Like I said, if you have a curve, right? The slope of this line is the same as the slope of this curve, the average slope of this curve. Okay. And here's a better picture of it. Let me see if I can. Geometric meaning of the average rate of change. So this blue line here, the slope is different everywhere, right? But if you're talking about between this point and this point, all right, the slope of this red line is the same as the average slope of the blue line, right? The calculus, right? Rates of change. All right, so here's another example. Instantaneous rate of change. So remember that example I was telling you about the guy running and you're shooting video of him, right? So instead of an average rate of change over a time interval, we want to know how fast he's moving at one instant of time. Okay, so what we do is we just let that time interval get smaller and smaller and smaller and smaller until it's practically zero. Okay, so here's this thing. This is a function s of t. It's going to tell us the distance the car travels once the light turns green, and its distance in time is given by 2t squared. So let's see what they want to know. They're going to want to know the instantaneous speed at a given time. So what they do here is they just give us this chart, basically. Y'all read that okay? Yeah. So they want to know at 10 seconds, what's the instantaneous speed at 10 seconds? Well, what we do is we look at the average speed from 10 to 10.1 seconds. And the average speed, according to the formula we've been using, is 40.2 feet per second. Okay. So now, but that's still an average speed, right? We want the instantaneous speed at exactly 10 seconds. So instead of doing from 10 to 10.1, we go from 10 to 10.01, an even smaller time interval, right? And we look at the average. And it's a little different. Instead of 40.2, it's 40.02. And it's like, well, that's close, but I still want the instantaneous velocity at time 10 seconds. I don't want an average. So it gets even closer. Okay, we'll look at an even smaller time interval from 10 to 10.001. And then we get 40.002. So you can see these are getting closer and closer to 40 feet per second, right? And you might like to assume that, well, how do we show that mathematically, right? We use limits. We'll take the limit. So what we're going to do is our formula here says we take S of 10, and here we're adding this tiny amount of time, right? So I'm going to add this tiny amount of time and call it H. All right, this is the same formula, but the time interval here is H. So that B minus A, all right, here's the B and the A, right? I want to smash those, right? I'm just going to make them real. So B minus A, that's that length. I'm going to call that H. So the difference between B and A, I'm going to call it H. So I'm going to take the distance at a little bit of time past 10 seconds and the distance at 10 seconds and look at that difference. And then I'm going to let my H go to 0. I'll let the limit of H goes to 0. That's going to give me my instantaneous speed right at 10 seconds. Does that make sense? All right, so what's the picture look like here? I got, I don't know what this looks like. Let's say it looks like this, 2t squared. So I could be like, here's A, here's B, here's f of A, and here's f of B. And let's say here's 10, okay? So instead of doing like this line, right, what I'm doing is I'm just going to do 10 and H. So this distance, 10 and 10 plus H. So that little length there is H. So I'm interested right here at f of 10, but I want to know the slope basically. I want to know the instantaneous rate of change at 10, right? The instantaneous rate of change at 10 would be the slope of that line right there at this point. So what I'm doing is I'm grabbing this and moving it that way, right? Blue. And I'm moving the B this way so I can isolate right there. The way I do that is I use 10 and 10 plus a little bit. All right. So this is still my change in Y. This is still my change in X. All right. And if I plug this in, again, our formula or function was 2t squared. Okay. So if I plug this in, let's see, limit H goes to 0. S of 10 plus H. This thing says take your input, square it, multiply it by 2. So I need 2 times 10 plus H squared. Now I subtract S of 10. Well, I replace the T with 10. All right. Now this looks kind of bad. I have H on the bottom. H is going to 0. I can't divide by 0, right? Every single problem we're going to do in here, we're going to divide by 0. All right. So this is how you do it. So we still have the limit here. The H on the bottom is going to go away, basically. On top, we have a 2. If we square this guy, 10 squared is 100. Then we have 20H. And we have H squared. And then we have to smash this. And then we have minus 10 squared is 100 times 2 is 200. And this is all over H. I still haven't taken the limit. So now I have to distribute this 2 across. 2 times 100 is 200. Then I got a 40H. And then a 2H squared minus 200 all over H. And notice the 200s go away, right? Look at this stuff. Everything has an H in it. Limit as H goes to 0. Everything has an H in it. 40H divided by H is just 40. 2H squared divided by H is just 2H. So we have 40 plus 2H. H is going to 0. So I'm just left with 40. Okay? That's how we do it. Right? You're always going to get an expression, and the trick is to figure out how to get the 8 on the bottom to go away so you can get a number. Right? So this told us what the instantaneous speed is at 40. I mean at 10. It's 40 miles per hour or whatever, feet per second, 40 feet per second. Okay. So that's the trick. But why did we pick 10? Right? Instead of 10, I could have said s of, instead of 10, I could just be generic. I could say just pick any number. A can be any time you want. Instead of 10 seconds, put A there. Now this will tell me the instantaneous velocity for any value A, right? We just did it for 10. Why do we have to put 10 there? We could put 8 there. We could put 6 there. We could put any number we want. So more generally, the instantaneous velocity at time A is given by that. Okay? That makes sense? All right. So the next step is, instead of getting the instantaneous velocity at a point, any point, why call it A? How about we just call it X? And this is going to give me the rate of change of S for any X. Again, this thing looks like that. We saw that at, actually it looks like this. Okay, we saw that over here at 10. We found the instantaneous slope there, instantaneous velocity. It's just the slope at that point, right? But then I said, well, let's just call this A. Well, then this thing tells me the slope at A for any A. Well, why don't I just replace that with X, and this is going to be a new function. Call it S prime of X. This is the change in S with respect to time. All right. So the slope here is different for every value of X, right? For this X, the slope is this. For this X, the slope is this. Like I said, if you have a function that tells you a distance at a given time, what we want is a function that tells us the velocity at a given time. And we want another function that tells us the acceleration at a given time, right? And this is how you do it. Right here, this gives you the slope. The slope is the rate of change. So this will be the next section though. But all it is instead of putting 10 for A, you just put X. You're going to get X. What you're going to end up with, well, they called it T. Let me call it T. I call it time. So at a given time. Basically, what you're going to find is that you're going to get 4T. So the rate of change of this guy, which was 2T squared, the rate of change of this guy is given by this guy. And we'll see soon how we get to that. All right. And if you plug it into that limit thing, that's what you're going to get. You're going to end up with 4T. Right. But in the meantime, let's look at more examples here. So here's your velocity. So if an object moves along a straight line with position S of t at time t, then the velocity at time A is that formula I just gave you. Okay. So it's just like the example, but instead of 10, we replace it generically with A. All right, so here's an example. Here's a function S of t. It's talking about, okay, something's moving in a straight line. It doesn't actually have to be moving in a straight line, all right? Think of it as a straight line. So the average velocity from 2 seconds to 4 seconds, okay? Well, the average velocity, we don't have to do limits here. We just do S of 4 minus S of 2 over 4 minus 2. Plug in a 4 for t, and then plug in a 2 for t. Subtracting, you're going to get 7. All right, so that doesn't need to use the limits. All right, that's the same as example 1 though. Looking at the average velocity over a given amount of time, right? Oh, the instantaneous. Part B, that's what we want. So what about the instantaneous velocity at exactly 4 seconds? What was our function? S of t is 2t squared minus 5t plus 40. All right, so if this tells us our distance at a given time, what is the velocity? What is the change at exactly 4 seconds? Well, what we do is we'd say, okay, let's take the limit as this little interval of time gets smaller and smaller. At 4 plus a tiny amount of time, and at exactly 4, and the change in time is, we'll call it h. So this is our tiny time interval. It's going to get smaller and smaller. We're looking at s of 4 plus a little bit, right? So at 4 seconds, and where it's at a little bit past 4 seconds. So this is just the distance it travels from time 4 to time 4 plus a little bit. So let's do the algebra here. We have the limit as h goes to 0 to, so we take 4h and replace the t everywhere with it. So we have 2 times 4 plus h squared minus 5 times the 4 plus h plus 40. Now minus s of 4. So everywhere there's a t, replace it with a 4. We have 2 times 4 squared minus 5 times 4 plus 40 all over h. We haven't taken the limit yet, so we have to keep writing it. So I have a 2 here, 4 plus h squared. 4 squared is 16, twice 4h, and the h squared. Distribute this across. So minus 20 minus 5h. Draw this 40 here. 4 squared is 16, times 2 is 32. 5 times 4, 20, and then 40 all over h. All right, let's distribute this 2 across. 2 times 16 is 32. Then I got 16 h's, and then I got 2h squared minus 20 minus 5h plus 40. Let's distribute this minus across. So minus 32 plus 20 minus 40 all over h. Now we can go like, those cancel, those cancel, those cancel. So what do I have left? I have 16h minus 5h is 11h's, 2h squared. This is all over h. So since everything here has an h in it, 11h over h is just 11. 2h squared over h just gives me 2h. Now if h is going to 0, that goes away, and I'm just left with 11. So the instantaneous velocity at exactly 4 seconds is going to be 11, whatever units they're using here. I don't know how fast, what units, oh, feet per second. So the feet per second. So they gave us a function that told us a distance at any given time, right? Well, from that we can find the velocity at any given time. The velocity is just the rate of change of the distance. It's also the slope. So that one at 4 seconds. So if we look at this guy here, oh, that's a different graph. Let's do what was it? 2t squared. So 2x squared. So we're looking at 4 seconds. Snapshot. Here's kind of a graph here. Let's do this. So 4 is somewhere around here. So whatever the slope is, the slope right there at 4 is going to be 11, right? So what we're doing is we're basically making what we call a tangent line, right? The tangent line at this point is a line that has the slope right at that point. Okay. blood flow. Okay, this is cool. 1.2 t plus 5. So the velocity of a blood cell inside of a blood vessel, right? It's saying the distance traveled in millimeters and where t is in seconds is given by this. So they want to know, find the velocity at time A. I don't even tell you what it is. I can tell you what it is right now. It's 1.2. How do I know that? This thing is linear. This is a straight line. There's no t squared to anything. If I graph this, it's going to look like that. Straight line. The rate of change is the same everywhere. The slope is the same everywhere. Right here is your slope. So it doesn't matter at what time. Its velocity is always 1.2 millimeters per second. Just by looking at it, I can tell you that. All right? Does that make sense? All right, well, let's do the math. So we want to know the rate of change. So h is go to 0. We want to do at time A plus a little bit, and then time A, and the change in time is h, and h is going to get smaller and smaller. So S of A plus h, we got 1.2 times the input plus 5 minus 1.2 times the input plus 5 all over h. And I forgot to write my limit there. So we still have the limit as h goes to 0, distributing the 1.2, got the 5, distributing the minus sign. We could see that goes away, that goes away. We're left with this 1.2h over h. We're just left at the limit. So there is no h here. H could do whatever it wants. We're getting 1.2, like I said, right? Makes sense? Okay, instantaneous rates of change. All right, here's just another example. So here's the formula, instantaneous rate of change. Tells you the rate of change at instant A, okay? And this is just another example of doing the same thing. So just plug it into the formula, then you get your answer. And the hardest part is probably going to be the algebra. This one is done with a calculator, okay? Y'all don't have like the mechanics to be able to do this like algebraically yet. See, the variable here is in the exponential, e to the whatever. So you plug this into a calculator. You could approximate it, right, by plugging in values really close, right? So find the instantaneous rate of change in 2005. Well, if 2000 is year 0, 2005 is time 5. So what you do is plug in values, or change in values really close to 5. So you do like f of 5 plus a little bit, and then like that for different values of h, you use h being like 0.001. So you look at like just past year 5 at year 5, or you could graph it and look at the slope, okay? Or you could just type into Google, find the derivative of f with respect to t at time 5. You'll get to all that vocabulary. It's just the same thing. Everything in here, the whole half the semester is slope. Everything's a slope and interpreting slope. Second half is going the other way. The second half is if I give you a function for velocity, can you find the function for the position, which is going backwards. So that's it for today, folks. See y'all Friday.